Well, the next one is exercise 4, and here we have a prime number p which is at least 5. We have to show that for such a prime, p square plus 2 must be a composite integer, and a hint is given, and the hint is that p must take one of the forms 6k plus 1 and 6k plus 5. So let's start the solution. From the Euclidean algorithm, we know that p takes one of these 6 possible forms. P is of the form six k or 6k plus 1 or 6k plus 2 or 6k plus 3 or 6k plus 4 or 6k plus 5. For some non-negative integer k, and this happens because when we divide p by 6, the integers are the possible integer is either 0 or 1 or 2 or 3 or 4 or 5, and accordingly we have these 6 forms. Now according to the given hint, this form and that last one are the only possible ones. That means we have to somehow rule out the other forms, and in doing so, primality of p will play a role. Okay, so let's see. If p is of the form 6k, then 6 has to divide p, which is not possible, because the only positive divisors of p are 1 and p itself, and 6 is none of them, since 6 is composite and p is a prime. Then if p, we'll of course leave 6k plus 1 because it's mentioned here. If p is equal to 6k plus 2 and hence is equal to 2 times 3k plus 1, then 2 divides p. This however can happen. Okay, 2 divides p. Had p been any prime, this would have happened, but we have this extra condition, right? P is greater than or equal to 5, and so p is equal to 2, which is also not possible. But instead of writing that, let us just club this with the other cases. If p is 6k plus 3, then 3 divides p, and so p is equal to 3. That is also not possible due to this inequality. And finally, if p is equal to 6k plus 4, then okay, we can continue this, right? Then again, this is 2 times 3k plus 2, then 2 divides p, and so p is equal to 2. So none of these above 3 cases is possible, because p is greater than or equal to 5. That is understood, of course, no need to write it again. Hence p is either 6k plus 1 or p is 6k plus 5, where k is some non-negative integer. Okay, now let's see what happens to p square plus 2 in each of these two cases. If p is equal to 6k plus 1, then p square plus 2 is this. Now if we expand the square, we would have 36k square plus 6 times 2 is 12 plus 1 square plus 2, that means 3. And we can take 3 common out and have this 12k square plus 4k plus 1. It's tempting to immediately conclude that this itself says, because we have two factors, right, that p square plus 2 is composite. But we should not be so fast, we should not be so hasty to conclude, because you see, there is a possibility of this factor being equal to 1. That's because k is a non-negative integer, so k can be 0. What will happen then? Then this factorization is not a non-trivial factorization. So it does not immediately say that p square plus 2 is a composite. So let's see what happens if this is 1. Now if that other factor, that is 12k square plus 4k plus 1 is equal to 1, then k is equal to 0. Note that ordinarily this you cannot conclude this, right? But because you know that k is a non-negative integer, so that means k has to be 0. But then what happens to p? P is 6k plus 1. If k is 0, then p becomes 1. An impossibility. So this cannot be 1, but its smallest value is 1, so that means it has to be greater than 1. And now we can conclude that because of this, p square plus 2 is composite. Okay, now let's see what happens when p is 6k plus 5. Then p square plus 2 in this case would be 6k plus 5 whole square plus 2. So expanding, we get first, of course, 36k square plus 2 times 5 times 6, that means 60k plus 5 square plus 2, 25 plus 2 is 27. And now from this we can take 3 common out, of course, and that leaves us with 12k square plus 20k plus 9. 3 times 9 is 27. This, however, does not have that same problem, because since k is non-negative, the smallest value of this expression 12k square plus 20k plus 9 is 9, or it is either 9 or something greater than 9. So this itself is a non-trivial factorization of p square plus 2. So here itself we can conclude, hence in this case also p square plus 2 is composite. So that means in general p square plus 2 is composite. So in this case also p square plus 2 is composite, and that's it. That is the solution. So let's see another one. Right, this one has 2 parts. Part A says this: given that p is a prime and p divides a to the power n, prove that p to the power n divides a to the power n. There is part B also, but let's just solve this itself. Okay, now there are some things. Nothing has been said about what a and n these things are, but of course they are integers, and that too we can consider them to be positive integers, because you see, if you take n to be 0, then it does not make sense. Does not make sense means in that case also, well, we cannot say so, no? In that case the hypothesis is false actually, because a to the power 0 would be 1 and p does not divide 1. So to be safe, we assume that both a and n are positive integers. That's it. Since p divides a to the power n, we have by that first corollary 1 to our fundamental theorem of arithmetic, that is, oh well, not fundamental theorem of arithmetic, but that other result, it is theorem 3.1. It is that theorem, do you remember? It says that, this theorem I am talking about, that if p is a prime that divides the product of 2 integers, then p has to divide at least one of them. And the corollary that we are mentioning here is that corollary which extends the scope of this by considering not just a product of 2 integers but any finite number of integers. That thing we have applied here, and any finite number, n number of integers, all of which are a, so p has to divide a. So this means what? Then A is equal to Kp for some positive integer k Well, if you want, you can assume A to be 0 also, assuming that A is non-negative, but it's understood that in that case this is trivially true. So we are assuming K to be positive, and as such A to be positive, and as such K is also positive. So this simply we have just raised both sides to the nth power, which just directly implies that p to the power n divides a to the power n. So that's what we wanted to show. Now let's see part B. In part B, it is given that a and b are two integers whose greatest common divisor is a prime. If this is the case, what are the possible values of this some other GCDs? GCD of a square and b square, GCD of a square and b, and GCD of, I believe it's a cube, a cube and b square. We often get confused when GCD is given, but always try to think simply as possible. Since the greatest common divisor of A and B is P, the only, watch this, okay, the only positive common divisors of A and B are 1 and B. Why though? How are we concluding this? It is given that the GCD of A and B is P. Okay, fine. So then we are saying that this implies that the only positive common divisors of A and B are 1 and P. How are we getting this? Suppose D is any positive integer that is the common divisor of A and B. It divides both A and B, and D is positive. Then from properties of GCD, we know that D has to divide P. Now this divisibility relation and positivity of D implies that either D is 1 or D is P. So that's how we are getting this conclusion. Hence, the only positive common divisors of a square and b square are. Now, can we think of this? You see, P divides both A and B, right? Because being the GCD, it's after all also a CD, a common divisor. So P divides both A and B. Okay, and that implies, you just look at this calculation in the previous part, that P square also divides A square and B square. P dividing A and B directly imply that P square divides both A square and B square. Alright. Now, is P square going to be the greatest common divisor of A square and B square? That is positive, of course. Suppose that D is a common divisor of A square and B square, which is positive. That is, D divides both A square and B square. If you are able to conclude somehow that D also divides P square, then by definition P square will be the GCD of A square and B square. Can you see how to do that? I can almost immediately see why that is the case, but can you see how to do that? You can of course not answer me now itself, but what I am going to do, I will just simply write what the thing is, and I will leave this part to you to figure out why what now I am going to write is true. One P and P square, and among them what is the greatest? Obviously P square. Hence, the GCD of A square and B square is P square. Similarly, from these other GCD values you will get a clue of how we are able to make these conclusions. The next one is GCD of A square and B. This will be P, and the GCD of A cube and B square, it will be P square. And in trying to figure out how we are getting these conclusions, you also concentrate on this only. Okay. Here, in fact here, not here, here, this only. These are the only positive common divisors of A and B. There can be nothing else. Okay, so that will play a role in these conclusions. So that is the solution. And let me just end the video here itself. Our next upload is this coming Friday, and on Friday we will go to graph theory. So see you on Friday with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.